Good afternoon, everybody, and I apologise for not being with you in person. I've been asked to speak about the RepRap project and about the implications for manufacturing in the world if the means of making things by self-reproducing machines becomes widespread. So I called my talk Manufacturing for the Masses, Manufacturing for Everybody. Now, if we're going to talk about manufacturing, let's start by looking at industry, and let's start by looking at the world's biggest industrial companies. According to Forbes magazine, the biggest company in the world is the International Bank of China, which has assets of 3.3 times 10 to the 12 dollars, which is a lot of dollars. Now, I should explain that not all of the numbers on this slide are directly comparable because some of them are assets and some of them are market capitalization. Anyway, International Bank of China, biggest company in the world. And we have to go down through 6 of the biggest companies in the world before we get to the 7th, ExxonMobil, and arrive at a company that actually makes something as opposed to merely pushing pieces of paper about or moving ones and noughts about. ExxonMobil is the first company in the world that makes stuff. And then if we carry on down the list, we find the first complete manufacturing company on the list is number 11, which is Toyota. And then immediately under them is Apple. Apple is sometimes called the biggest company in the world. It has the biggest market capitalization, but that doesn't quite make it the biggest company in the world. So these are the world's biggest companies. And the reason why I've mentioned them is because there's something strange about the world's biggest industry, which is on the next slide. This is the world's biggest industry, according to Forbes magazine again. It's farming. And this prompts a very interesting question, which is, why are there no farming or food industries among the world's biggest companies if this is the world's biggest industry? Well, we'll come back to that question in a little minute. Let's go back to manufacturing and look now at global manufacturing output. And you can see the pie chart here is divided into 2 very unequal regions. There's the enormous blue area, which I call P, and I'll explain what P means in a moment. And that is 5 times 10 to the 12 metric tons per year of manufacturing. This is a rough figure. It's something that I had to deduce by doing various calculations from other statistics, and so it's not to be taken as being wonderfully accurate. And then this tiny, I'm pointing at my computer, let me point on the screen, tiny little orange sliver, which I call EP, which is about 1,000 times smaller. And that's a tiny little bit of manufacturing which is distinct from the type which I call P. Now, what are these 2 types of manufacturing? Well, they're these. P stands for phenotype, and it means bodies of living organisms. And the natural world is the thing that manufactures most in the world. EP stands for a biological idea, the extended phenotype. What an extended phenotype is it's something made by a living organism that is not its own body. So, for example, on the left we have a bird's nest. Birds' nests are part of the extended phenotype of birds. On the right we have a motor car. Motor cars are part of the extended phenotype of human beings. And these things get made. Termites' nests get built, birds' nests get made. These things in the world are a tiny, tiny amount of the manufacturing in the world. So we've got these enormously unequal types of manufacturing, organisms making themselves, and then those organisms making other stuff. From which we can deduce the following, something which we probably knew already, which is that self-replication allows vast wealth production. Self-replication is what's going on with the living organisms making themselves. Their cells are dividing, they're reproducing and having children. And I contend that this is the reason why agriculture and farming don't feature in the world's list of biggest companies. Agriculture and farming are entirely concerned with things that copy themselves, wheat and cows. And because those things copy themselves, it keeps farming distributed in small units because everybody can do it. Anybody can grow a seed, and so it's very easy to get involved in any sort of agricultural production, and that keeps small P actors coming in at the bottom and keeps the industry distributed and diverse. And so the idea of economies of scale in agriculture don't mean as much as they do, for example, in the motor manufacturing industry. So, given these facts, if indeed the second one is a fact, as I say, it's a conjecture of mine, really, how can we put the power of self-replication to make things into the hands of everybody? And that's really how I came up with the RepRap project, a project to make a self-replicating manufacturing machine. The RepRap is short for Replicating Rapid Prototyper, and it's a partly self-replicating 3D printer. And the picture on the left-hand side of the screen there is of one of the latest RepRap designs. It's called the RepRap Snappy. It was designed by River Desamara of the Bay Area RepRap Users Group in San Francisco. I've never met him, incidentally. And it's a self-replicator. It prints about 80% of its own parts, which is a pretty good proportion. Now, a self-replicating machine would be interesting, of course, but it wouldn't be very useful unless it did something else as well, just as wheat or as cows do. Wheat self-replicates, cows self-replicate, but wheat makes bread for us, and cows make milk, and also beef. And so they do something in addition to self-replicating, which is useful to us. RepRap, in addition to copying itself by printing parts for another copy of itself, also makes other useful goods. So that is the reason why RepRap is useful in the same way as agricultural plants and animals are useful. Now, we've got a 3D printer. Why choose 3D printing to do this rather than, say, making a self-replicating lathe or a self-replicating laser cutter? Doubtless that could be done as well, but 3D printing is a unique manufacturing technology, and I want briefly to explain why that is the case. So, why is 3D printing such a uniquely powerful way of making things? I say powerful. It's second only to the first thing I mentioned, which is self-replication in nature, cells copying themselves. That is the most powerful way of making things we know. RepRap is a self-replicating machine, but it doesn't do it in quite the same way as biological organisms do. Let's look at 3D printing. RepRap is a 3D printer. Why is it so powerful? Is it fast? Well, no, not really. Anybody who's used a 3D printer knows that it's not a particularly fast process. Is it cheap? Well, yes, 3D printers now are very cheap, thanks, if I may say so, to the RepRap project, which was the first of the low-cost 3D printers. But really, to know why 3D printing is so powerful, we have to ask a second question, which is, how can the shape of stuff, how can the shape of things we might want to make be complicated? And complication turns out to be complicated in itself, more complicated than people who think in terms of complexity theory perhaps think. In terms of geometry, when we're talking about shape, complexity can have three forms, which are all independent of each other. And that's illustrated by this picture here, which is a three-axis graph, as you can see, in Cartesian space. The horizontal axis along here, that's what most people mean by complexity, certainly in the computer industry. It's combinatorial complexity. It's the number of bits that something has in it. So a triangle just has three sides, whereas a gear wheel here has many, many teeth. So that's has got more bits in it than the triangle. But there's a completely independent type of complexity, which is analytical complexity. The triangle is made from straight sides, but we can have complicated curves. And those complicated curves have more difficult analytical expressions used to describe them. And finally, we can have dimensional complexity. The triangle is a two-dimensional object. The gear wheel is a flat object. It may have some thickness, but there's no detail in 3 dimensions. If we go up into 3 dimensions, shapes can get more complicated because they have 3-dimensional structure as opposed to 2-dimensional structure. Now, anybody who's done any computing knows that dimensional complexity is the thing that really makes things difficult inside a computer. A one-dimensional problem is orders of magnitude easier to solve than a two-dimensional problem, even if the combinatorial complexity of the second is actually much less. So, let's look at the conventional way in which we go about making things, which is to cut them out. And here's a picture of a turbine impeller with a numerically controlled milling machine cutting it out. And this is the tool of the milling machine. And the tool, the yellow bit of the tool here, has got to move over the surface of this object in order to cut it out of a solid block. Now, it turns out that in order to solve that problem, we have to solve a 5-dimensional problem. There are the 3 dimensions of space, left, right, forwards, backwards, and up and down, but in addition we can rotate the cutting head of the tool about a further 2 dimensions to give us 5 dimensions in total of the freedom of movement of the cutting tool. Freedom of movement in 3-dimensional space is normally 6 freedoms, of course. There's a 3rd rotation, but that's the rotation about the axis of the cutting tool itself, so we can forget about that one. But in order to figure out how to move the machine around to cut this shape out, we have to solve a 5-dimensional problem. And that 5-dimensional problem is incredibly difficult to solve inside a computer. Indeed, we know that there are shapes that computer-controlled machines such as this can cut, but which we cannot tell them how to cut because the problem is too complicated to solve. So the limitations of the technology are not the physics of the machine itself. The limitations of the technology are inside our heads or inside our computers. How do we instruct it to move in order to achieve the result we want? Now let's look at 3D printing, making a similar object. If we have a 3-dimensional object to make in a 3D printer, the way the 3D printer works is to slice the object into 2-dimensional slices. And now, immediately, we've taken a 3-dimensional object, which before gave us a 5-dimensional problem to solve, and now it gives us a 2-dimensional problem to solve, which is very easy. We can solve that sort of problem with the software that we use for processing images and all sorts of other things like that. So, solving that problem is utterly easy compared to solving the problem of how to cut the object out using a cutting machine. And it is for this reason that 3D printing is so powerful. There is no restriction on what we can make with a 3D printer imposed by our ability to control it. The only restrictions are imposed by the physics of the machine itself. The machine can make anything of which it is physically capable of making. Okay, so that's why 3D printing is so powerful. And we've got a 3D printer, RepRap, which is designed to print copies of the parts of itself so that somebody else can make one. And we know, of course, going back to my agricultural description briefly earlier, that anyone with a plant can grow a seed for a friend. And this is very easy to do, and it costs the 2 parties involved virtually no money to do this, and very little time, because the seed just grows itself. And similarly with RepRap, anyone with a RepRap machine can make another RepRap for a friend. And the reason for this is the RepRap project is entirely open source, so all of the design files, all of the software, all of the documentation, all of the electronics is all completely freely available to everybody, and this means that anybody with one of the machines can use that information to create another one, and they don't have to pay any royalties. All they have to do is to pay for the raw materials required to make it. So here's a picture, in fact, of the very first time that a RepRap machine reproduced. I'm on the left with the very first RepRap machine we ever made, which we made using a conventional 3D printer, not a self-replicating one. And on the right is Vic Oliver from New Zealand with the very first child machine that we ever made. When we assembled the child machine, we put it all together and we plugged it in, and sadly it didn't work. But the reason it didn't work was nothing to do with the RepRap machine making parts for itself. It was because we very stupidly cut one of the drive belts too long a length, so it's too slack. And it turned out that if we just held a screwdriver against the drive belt, then the child machine, on the right there, the child machine worked perfectly. So what we did was we immediately designed a belt tensioner, and we held a screwdriver against the belt of the child machine and had the child machine make that belt tensioner as its first grandchild part, fitted it to the machine, and then it worked perfectly. So the very first act of the machine was actually an act of self-improvement and self-repair. And of course, with self-replication, self-repair sort of comes free, which is another great advantage of the replicating technology. Okay, let's have a little look at the economics of this now. We're all familiar with the idea that goes right back to Adam Smith, if not before, the idea of economies of scale. So here we've got a traditional manufacturing operation consisting of a blacksmith's forge, where somebody is beating out some metal and somebody else is running the forge and so on. A small-scale operation, every village would have had one in pre-industrial times in order to make gate hinges and horseshoes, of course, and other small iron objects. And on the right is a photograph of a 19th century iron foundry. And that iron foundry is essentially doing the same job, But of course, it's much bigger, and it can make parts for use as hinges or as horseshoes much more cheaply because of economies of scale. The organisers of the iron foundry can have somebody specialising on doing the accounts, somebody else specialising on doing the marketing, somebody specialises on keeping the furnaces running and so on. Because we've got that diversion of activity and specialisation, the whole operation becomes much more cheap to run, and so the products can be made much more cheaply. And we're all familiar with the idea of economies of scale. I mentioned Toyota earlier. Toyota, of course, have among the biggest car plants in the world. That's a real good example of economies of scale, because it would be impossible to make motor cars so cheaply were it not for the case that those car plants were so enormously large. But things don't always work that way. Sometimes we get economies of distribution. So again, in the 19th century, this is a picture of a 19th century laundry. And our grandparents and great-grandparents, when their clothes got dirty, parcelled them up and sent them away to a laundry, and the laundry would clean them, and they would come back in a parcel 3 days later, and that was all good. But nobody does that these days, because we all have a robot. We all have a robot in our kitchen to do the job for ourselves. And that robot has a number of interesting characteristics. After the fact that it washes our clothes, the most interesting characteristic is that we're perfectly happy for that robot to sit in our kitchens idle for 95% of the time. We've invested capital in it, it washes our clothes a little bit of the time. Most of the time, it does absolutely nothing with that capital we've invested in it. And the reason we're happy with that is because it's not a very expensive robot. If it's cheap enough, we're happy for it to do nothing for the convenience of local washing of our clothes. The system also for washing our clothes is much more robust than the 19th century laundry. If the water supply to the laundry fails, the whole town has dirty clothes. If my washing machine robot fails, then I just knock on my neighbour's door and say, I'm waiting for the washing machine to be fixed, could I borrow yours? And they say, yes, of course, no problem. A distributed system is inherently more robust than a centralised system, and that's another big advantage of it. And we're beginning to see this appear in other areas too, and we'll see some more examples in a minute. For example, the electricity being generated to allow me to talk to you now is almost certainly being generated in something like this. This is a 2 gigawatt, in fact this is a gas-fired 2 gigawatt power station. But of course, increasingly, we have our own little power stations on our roofs gathering sunlight and powering our own homes individually. And again, all the advantages of robustness against damage come with this distribution of generating capacity. That's not quite economic at the moment in the way that, for example, a washing machine is economic. It still has to have a little bit of government subsidy, but that subsidy is very rapidly diminishing as the cost of the solar panels comes down with the increase in manufacturing. And I showed you a pie chart earlier, which I said had some numbers in it that were perhaps not wonderfully accurate. This is an accurate pie chart. It's taken from a piece of peer-reviewed research at MIT, and it's on the annual UK research and development expenditure on consumer products. And by consumer products, I mean things like toothbrushes, children's toys, and so on. In other words, the contrast between them and perhaps the building of roads or the building of office blocks and so on. Those are not consumer products. £5.5 billion in the UK is spent on consumer products every year. And again, this divides into a pie chart, and we've got a blue area here this time, which is £2.3 billion, and a rather larger orange area, which is £3.2 billion. The distinction between the two parts of the pie chart there, the blue chart, the smaller one, and the orange part, the larger one, is a very surprising one. It's this. The smaller area is the expenditure by industry, and the larger area is the expenditure by private individuals. Individual people putting up shelves in their home, repairing their own children's toys, making things for themselves. And you would expect this to be much smaller than the research and development expenditure by industry, but in fact it's not. And the reason it's not, of course, is because simply there are many, many more people than there are industrial companies. And this is a really surprising result. So taking this idea of distributing industrial activity right down to the level of individuals, what can we say might happen in the future? Well, today, everybody in the developed world, we all have our own CD pressing plant, we all have our own photographic laboratory, and we all have our own printing press. Of course, they don't look like these traditional versions of those things, they're all incorporated into our computer. But nonetheless, we've taken those industries and we've taken them back to ourselves. And so, what might happen in the future? Well, in the future, if we do all these things for ourselves, why shouldn't we have our own factory? The RepRap machine would be a good start for that, perhaps. And if we're going to have our own factory, let us take advantage of that enormous industry that was our very first industry, that is entirely based on self-copying, farming, and have it be a factory that makes more factories. Anyway, that's all I have to say. If you want to know more, point your phones at that. And I'm pleased to say that I've agreed to answer some questions, and you'll see that next. Thank you very much indeed.
So the first question we wanted to ask was that when you first conceived the RepRap, it was, as you explained, a self-replicating machine.
Yeah.
But it so happens that most of the RepRap machines in the world today have been made from open source specifications and a set of all the parts and components. So actually, that can be interpreted as the great success of open source concept.
Mm-hmm.
But also, it's slightly different from your original physically self-replicating machine. So, yeah, what do you think about this turn of?
Yes, what you say is unquestionably true, and that point I made about economies of scale, of course, is to a certain extent in competition with the RepRap concept here. It is still the case that it is very cheap to produce stuff industrially because of economies of scale, and lots of people have started making kits for RepRap machines, some of them not self-replicating at all, and those kits can certainly compete economically with RepRap at the current time. But of course, it's got to be the case that as the technology improves, self-replicating systems must take over. And we sort of have a proof for that, but going back to the agricultural example again, if we take a single seed is far more complicated internally than any machine ever produced by a human being, and yet it costs nothing at all. And eventually, the self-replicating machines will get to the point where they are so incredibly cheap because of their ability to copy themselves that no conventional industrial process will be able to compete with it. But I fully agree with the premise of the question, which is that at the moment we're not quite in that position. But conventional manufacturing can only ever progress by an arithmetic progression, whereas self-replicating machines necessarily progress by a geometric progression. And a geometric progression, no matter how slow its rate constant, inevitably overtakes an arithmetic progression, no matter how fast its rate, eventually.
So the second question comes from Hiroya. And so he said that I personally bought a RepRap Huxley back in 2011. Once I plugged the machine into AC 100 voltage, soon an electronic board started to make a smoke.
Yeah.
And the board was burnt out. I replaced the board with a new one and I could fix it. In the end, I could run the machine. I enjoyed all the process of fixing it because I'm a geek type researcher.
Yeah.
However, if ordinary people met this type of an accident, they would never believe open source hardware machines. Especially in Japan, we have very strict common expectations and legal system for keeping quality and security of products.
Yeah.
How do you think quality control, quality assurance of open source hardware? Do you think we have to make new kind of legal system or some license agreement between makers and users?
I'm not sure about that, but just to go back to the difficulty with the circuit board and so on, as you can see by looking at me, I'm horribly old. I can remember when microcomputers were first introduced, and of course they were exactly the same. When we got the very first microcomputers, they consisted of little more than a single circuit board with a separate keyboard on a piece of flying wire, which didn't even have a plastic case around it. And those were entirely for geeks, and we all loved putting them together and making them work. And they were not a consumer product in the general sense at that time. Computers are now, of course, a completely ordinary consumer product, and as a result of that initial experimentation by those geeks. And 3D printing is now more or less in that stage that computers were 30 years ago. And so we'd expect to see the progression like that. Now, your question about a legal framework is an interesting one. I suspect that it's going to be very difficult to try and fix this sort of problem legally, and it will be much easier to fix it in Darwinian terms. Let me explain what I mean. The problem with the law is that the law has to have something to attach its control to. And if you've got an activity which is being carried out by millions of people all over the world, it's almost inevitably, as a consequence of that, impossible to regulate. A good example is the copyright in music. We all know that music is copyright, but equally every 17-year-old on the planet has 30 gigabytes of illegal MP3s on their hard drive, and there's nothing the law can do about that. The law is impotent in the face of that sort of thing. Now, I suspect that personalized manufacturing will be much the same as the illegal copying of music. I'm not saying it'll be illegal. There's nothing illegal about making something for yourself, or indeed making something for somebody else. Trying to constrain that legally and in terms of legal quality controls, I think will be very difficult though. But because you've got this enormous pool of competition of people all trying to do this or all doing this successfully, the Darwinian effect of the most successful ones coming to the top will inevitably come to dominate. And so we'll discover that the best makers are the ones that get the best reputation, just as the best sellers on eBay get the best reputation, and as a consequence people will go to them to get things made if they indeed don't want to make themselves. So we've got an automatic system there which ensures quality control by means of reputation and the interconnectedness allowed by the internet and so on. And I suspect that that'll be a much more powerful form of regulation than the mere passing of laws.
So the third one is that has to do with the biomimetics.
Ah, yeah.
So we all know one of your major interests as a researcher is biomimetics, and aside from RepLab, the self-replication machine, do you have some other ideas for the future biomimetic engineering or design? Also, we are very interested in your new projects, if there's any after RepLab. What kind of biomimetics are you interested in?
Well, there are a number of things. I already mentioned one in my talk, just in passing, when I said that 3D printing was our most powerful manufacturing technology, but I said the way in which organisms grow is even more powerful still, with cells copying themselves and arranging themselves to form a body, or a body of a person or a plant or whatever. It seems to me that there's an enormous biomimetic area in moving manufacturing in that direction. And my friend and colleague Neil Gershenfeld at MIT, I know, is working on this, as a number of other people, George Whitesides at Harvard, for example. They're all attempting to set up systems where we have self-assembly at the microscopic level, making macroscopic objects in much the same way that organisms grow, indeed mimicking the way that organisms grow. I think that that is a fascinating area of biomimetics, and certainly one which will become very predominant in the future. My own personal ambitions are a little bit more modest. It's not really a biomimetic invention, but I am interested in making horticultural robots. I'm interested in robots for automatically tending and tilling areas of soil, growing plants, and so on. keeping them free of weeds, and that sort of thing. And so that's an area in which I'm investigating. Now, of course, that's not really biomimetics, except that the robots may well have biomimetic elements in them, and those robots will also be made by RepRap machines, and so given that RepRap's biomimetic, that biomimetics comes in there as well. And finally, it's dealing with biology, namely growing plants. So that's one of the non-RepRap things that I shall be doing in the near future.
So the final question is about our project. So we got a financial support from a Japanese ministry, and our project is called Center of Innovation Project, Kansei-based digital publication. Kansei being some sensibilities and senses. Several researchers, some of us are still creating new publication machines based on RepRap. And we are going to make our project open source because we really admire the concept of RepRap.
Thank you.
Do you have any advice or suggestions to us as RepRap enthusiasts? What types of research activities do you want us to carry forward, both in like academics and industries?
Okay. I wouldn't like to tell you what research to do yourselves, but I do have some advice on how to organise an open source project like RepRap. And that's this. The first thing is that you get a wonderful flood of information which you wouldn't get if it was just a small group of researchers working in a laboratory. If you open source something, you create wikis and blogs and so on so that anybody can put information in, you will discover people all over the world start to contribute. And that really is the most powerful and useful of inputs to any research project. The most important things are often things where a person just contributes one apparently small idea, which turns out to be a radical idea. And also you'll get people who get really enthusiastic and contribute 100 ideas. In some ways they're all equally valuable. And of course, wonderfully, they're all free. I used to boast that I was running the largest research project in any British university when I was running RepRap as a university project, because the staff that I had was numbered in the hundreds. I wasn't paying any of them. They were all doing it because we gave the information away free and they were happy to contribute back. And so that's really a great bonus of doing any open source project. One of the things you have to be a little bit careful with is what we might call the administration and organization. And I'm probably not very good at this, to be honest. But you will find that some people want to volunteer for the project who, strictly between ourselves, are not all that helpful and indeed may hinder things, and you have to be rather diplomatic in dealing with that sort of problem. Occasionally you'll simply get crazy people who want to help, and you have to be equally diplomatic at dealing with that problem, and it's probably a good idea to have a plan for that sort of thing in advance. So that's another piece of advice there. And finally, of course, publication. As with any university research project, you have an obligation to publish the results for the benefit of the world, both in peer-reviewed journals and also, of course, in electronic form, as I've already mentioned, on the blog for the project, the wiki for the project, whatever you might want to set up. It's quite useful. One of the things we did when we wrote journal papers on the RepRap project was actually to have quite a large number of authors who were just people all over the world who were involved and who contributed something to the paper. And they weren't necessarily academics. We had papers appearing with authors on them and just a private address with no affiliation at a company or a university or anything like that. And I think that's a good thing, and I would encourage you to publish in learned journals in the same way. So there we go.
Thank you very much.
Okay, it's been a pleasure.
Thank you very much. The interview was done by Dr. Tomoaki Watanabe. Just for your information, I just made this a comment. And then we'd like to invite Dr. Tanaka, please.
Well, thank you. I will be making the following presentation next to the presentation that you just heard. So we've been talking about making things using 3D printers, and it can virtually get to the commercialization stage. But it does have philosophical, academic implications as well. When I first came to know about this, I thought it was quite strange. I had an eerie feeling, because come to think of it, look at the things around us, all the tools around us. But all the tools have been made by other tools, and that tool making machine was also made by other tool making machine, and it goes on and on. It just goes through cycles, and we track down to the stone tool. So tools were used to make another tool, and another tool was used to make even another tool. There has been the repetition or succession of events which are taking place to this day. So in the philosophical term, we call it a favel or homo faber. And we are the animals who makes tools. And fab is included in this word term of homo faber. And I was quite impressed by it when I first discovered this. So tools making tools, I've been talking about. Now let's talk about our future. So tools would evolve to make further evolved tools, and even prior to the inception of COI, we've been working on this. So for the very first time, RepLap was made for the first time way back, and using the RepLap, the resin-made parts, half of them were able to be made using that 3D printer. And for the very first time, as you heard through the first section of the lecture, there are good things about the 3D printers, because in front of your own eyes, you can share the experience of making things together with a maker. It's not that something was invented far away and it comes to you eventually. You don't know how it was made. You know it if you use the 3D printer, because you are there on the spot physically. So you get more familiarity with the product made naturally, more attachment. And many 3D printers are now available in many different models, but it's not suitable for every occasion, because look at the Japanese housing and American housing spaces and size are so different. And look at the diverse venue, be it schools or hospitals or workplace, place these 3D printers, and product made out of that may not exactly fit nicely with the space that you have. It happens quite frequently. So hardware can be made by 3D printer, but design drawings are made open on the internet, and you can modify them and tweak them to meet your exact needs in terms of size and functions and so forth. You can do it like that. In my lab as well, researchers are working, centering around Masuda-san. We sort of tweaked the RepLap to fit our own space. That's where we started from. So in order to make something that you wear, you have to be careful. Maybe the 3D printer available is too small. So we made our own and developed our own kit for the 3D printers ourselves. And prosthetics are now being made using our 3D printers. So please look at the video, which runs for about 3 minutes.
これは途上国の障害者への強い偏見と相まって貧困を加速させる原因の一つになっています。義足は通常プラスチックや金属などのさまざまな材料を一人一人の体に合わせて加工して作るハンドメイドの製品です。フィリピンでは最も安いものでも2万円ほど。これは現地の人にとっては手が出ないような値段です。また義足を作るためには多くの機械を揃えて使いこなすことが必要で、途上国ではこれは簡単ではありません。私たちはたくさんの人が手に取れるような安価な義足を作りたいと思いました。そしてそれを使う人が自信を取り戻せるような美しい、そんな義足を作りたいと思いました。 患者さんの切断していない方の足を 3D スキャニングして、それをもとに 3D プリンターで作る義足を開発しています。これは患者さんの体にぴったりフィットして快適で、また自分の足のような美しい義足を作ることも可能になります。この義足を実現するために私たちが開発しているものは大きくは3つあります。1つ目は義足の構成。これは体に触れる部分や関節部分に柔軟性のある柔らかい材料を組み合わせた新しい 3D プリンター義足の構成です。2つ目は 3D プリンター。通常の 3D プリンターでは出力が難しい柔らかい材料を出力するためのもので、コスト性、メンテナンス性を向上させるために途上国で調達できる部品を使って義足用の 3D プリンターを設計しています。そして3つ目としてソフトウェア。医療関係者や技師装具士さんが最小限の知識で義足のデータを作ることができる義足用の 3D モデリングソフトウェアです。私たちはこのプロジェクトをまずは日本から近くてファブラボのあるフィリピンやインドなどの 1,2 カ国程度で製品化をスタートさせて、最終的には全世界の途上国とルーラルエリアに広げていきます。
このようにですね、やはりこの
As you have seen, it all depends on what product you would like to make. Make it from the original materials. 3D printers can make anything that you like almost. Now, what about bigger things we may make? Higher height, having a higher height. And this is what is being exhibited at the foyer. The height is 2 meters and 20 centimeters, which is a bigger scale RepRap. I hope you have taken a look at it. It uses biodegradable resin, and center is hollow, and anyone can transport it. It can be a construction block, and it can be combined together like this, and apart from humans, animals, and insects, and the others, it can co-live together, which is a kind of a new architectural structures. So we know we can make it big, then conversely, we should make it smaller as well. So how small can we go with reduced cost? And we have done the research on that as well. This is available $70, less than 10,000 yen, small scale 3D printers frame section. In my university, one student is given this frame part, and this is the protruded part, extruder, can be put, and out on the ground, the 3D printers which can be used on the field can be developed, and this is what students have been encouraged to do. And any combination of the material will do and make it smaller, which can fit the small Japanese housing, like on top of the bed, you can place it. Very small scale 3D printers and so forth. And one more point. This is a part of our research activities, which is a core activities. Well, so far, 3D printers are making something in a 3D form using the source material. But from now on, maybe electronics parts and sensors and the batteries can come in so that it can exhibit electronics properties, and it can produce digital information like a fabricator. So it's not only a mere manufacturing, but it can be offered as a part of the services. So this is the other step that we are hoping to achieve. And this is a first trial. Using a type like this, prototype. and it can be individually controlled and managed. So this is an individual piece, and something like this can be made, having a unique ID on its own. And internet URL can be linked together on the internet. Then it used to be just a mere thing, but now it can be combined together with the services. Something like IoT. Just for example, it's a very simple demonstration. We have a smartphone in our hand which can be waved on the thing. Then you can tell when this was made by whom, using what material. The authorization, has it been certified? What about the product assurance and guarantee and so forth? All the information which needed to be imprinted into the product per se can be retrieved by a smartphone screen. So this is the very first step toward IoT that we done. Not only the tagging, but we looked into the peripherals like temperature, human behavior, pressure, and so forth. So peripheral information could also be tracked and detected by using sensors, and the information also can be embedded. So we've been talking about the fabricators. So 3D printers can evolve into being a fabricators, and at the very outset, as I said to you, it's not mere production of things or the goods. After the goods have been delivered to the user, further services can be created when will be born, and users can make wider use out of that product. And the data can be analyzed so that one person's characteristics and creativity can be analyzed further. So wealth of information needed for making analysis and analytics can be captured like this, because these three elements go in cycles. So sensors and the parts can be incorporated into the product. And maybe the waterproof kind of skeleton might be needed. This is what is being distributed. It's not that it doesn't have that performance at this time. And JSA made this as a commercial product called Fabrial, which is a filament. For one thing, it conforms to the international standardization ISO standards, like cytotoxicity test and skin stimulus test. They cleared it, highly safe, very reliable, and you can use it. It's waterproof, tight. As you see on this video, inside liquid is put in, but no water leakage. And it's quite soft. It dense with a finger, and battery and many things can be inserted inside this container. It can be placed outside or maybe used inside the water as well. So in this way, we are incorporating sensor technology to the product so that we can make further prosthetics and other things. At the same time, for each individual, they have body characteristics, and we need to meet that specifications of each individual and make a product. You have seen the neatly produced video, but on the forefront, everything doesn't work that neatly. Data filing method is different from each stage, and it is often that the data gets ruptured and broken, so it takes a long time to process the data. In order to overcome that difficulty, Fuji Xerox, we worked with them, and from the scanned data, right out to the output stage in an integrated fashion, we worked to develop a software called VoxFab. We are still working on it, and by June, we hope to make this open on the internet free of charge. So far, out on the ground, we've been working on the personal fabrication technology, making just one piece only, but which does not fit for the mass production setting. But for the number of years in the past, we've been trying to identify where our invention might have use. There are areas where people will not get satisfied with a mass-produced product like cosplay and hobbyist. Thinking about myself, I also see that this might be it. And at the same time, there is a person with a disability or the welfare area where mass-produced goods will not fit. There might be a niche there for making things using the 3D printers. So we have two areas at hand, and looking at them, the research will continue. But right at the center of the community and society, the areas are coming up where further needs can be identified, which is a visiting nurse area. Right at the center, these kind of needs would arise. What does it mean by that? Well, this is a COI concept, which is backcasting, like 2020. What would be the society like in Japan? We've been thinking about it. So this is a visiting nurse application, and Dr. Miyagawa taught me a lot on this field because she's an expert. By 2025, about 400,000 people cannot enter the hospital, and end-of-life care cannot be given because of that. And 60% of the Japanese people wanting to have a home-based therapy and care, like to receive care at their own home. That's their wish. So this has to be complied with. But look at number of visiting nurses available, very small. There is a shortage of a body of visiting nurses. And we cannot picture exactly what it would be like to receive a visiting nurse's care. So 3D printers and the digital manufacturing can play a role here, because home setting is different from the hospitals, so that how the handhelds, arrangements are placed, and shapes and forms of the beds are different from one home to another. And every day, of course, the person who needs care has to be cared. This is a setting for the visiting nurse. So like a do-it-yourself time, suction tools will be devised on the spot and so forth. So many ingenuities have been exercised, but unfortunately, it has not been systematized, although individual inventions and modifications have been made for the needed tools and so forth, and the findings have not been shared. So everyone has to start from scratch, trying to come up with better, easier to use tools for the patients. So maybe the original idea can be shared, first of all, on the internet, so that one can come up with a follow-up, trying to introduce a modification idea to make that invention better. So this is something we can picture for 3D printers to do. This is a suction machine. There are so many cables and feeds which are connected with the patients. It can get very complicated. And it's better to have a suction feed fit perfectly with the shape of each and individual bed. You like to write your own love letter yourself, right? And we can make some aids for that. Aiding machine or visiting nurse beforehand. Or will not touch the body of the patient directly, abruptly. First of all, she gets training herself before going on to the patients. She just rehearsed it using the model like this to place a suction tube into the nose cavity of the patient, and visiting nurse can train herself beforehand before having direct contact with her patients. So something like this can be done more intensively in future. So in a research group, we are bundling together all the technologies and try to apply this FAV technology to the nursing care setting. And we hope to expand that using the coming 3 years. So this is the conclusion summary. We would like to make something nearer to the user's site. So we like to modify RIP-RAP based on the open source 3D printers to fit to every setting, to accelerate the speed, make size variable and the structure variable. We done that. And also IoT direction, inserting RFID tag and inserting sensors. And thirdly, we are working on the materials as well to conform to the standardized safety test, like we'll be making it waterproof. We done that already, and as a result of backcasting, we thought that area of visiting nurse will become very important in future. So we hope that we can apply this technology to the society practically. So this is it from me. So let's move on to Professor Furukawa from Yamagata University to expand on this scenario further. What would be the application at the local area in Japan? Food, staff, and software-related area, and so forth. Let's hear him talk about that. Thank you.
Thank you very much, Professor Tanaka. From Yamagata University, Professor Furukawa. Well, Professor Tanaka already introduced him to you. So, Dr. Furukawa. Thank you for your introduction. I'm Furukawa, as was introduced. I'm with Yamagata University. I specialize in material research. Dr. Adrian Boyer gave the presentation, and he mentioned that these 3D printers are now become cheap. I didn't bring it with me, but according to some news, with regard to how fast 3D printers can print, there's a benchmark chart. In the past, in order to evaluate computer performance, those were used, but now 3D printers, just like computers, they have become a commodity. It has become one of the tools. So against a backdrop, here in Japan, about the implementation or the installation of 3D printers in the society. In this regard, Japan seems to be lagging behind. So how best we can really move ahead? That's one of the things we're doing in the project. Yamagata University is located in the rural areas. Regional revitalization has been one of the themes. In the Monozukuri Manufacturing White Paper, as one of the efforts for regional revitalization, Yamagata has been quoted as sort of number one. Yamagata Manufacturers Network, Yamagata Makers Network, YMN, has been organized. I didn't do it alone. The people from the local community took initiative when they saw the prevalence of 3D printers, and they came up with this idea that perhaps the rural areas might need such people. It's not the university, but the technical schools, the teachers came up with the initiative. In Japan, there is a kind of a system to foster engineers in the regions. At the university, what can we do? On the second floor of the railway station, we created this fab. this university, even located in the rural areas, and when we say we want to have people come over, people are not that cooperative. But on the second floor, this is a kind of a multi-purpose room. It says open space here. And we were allowed to use this space. The Professor Tanaka also came to look at this. I wouldn't call this Fab Lab, but 3D printers, laser cutters can be installed. The MEXT, the Ministry of Education, gave us support. This is really the science, sparkling joy, and with inspiration. The results from researches should be shared with the middle school, the junior high school students, so they can experience the results of our researches, and we can hold an event. August last year, we did this in the Station Fab. Do you know 3D printers? That was one of the messages. Together with students and our staff, we had this discussion. Just saying 3D printers wouldn't be attractive enough. 3D jelly, let's make 3D jelly. So you make something sweet. So we are invite these junior high school students to come up with molds for jellies. Among some junior high school students, some of them are really good at using computers. We put them into several groups, and first they draw something and then put it on the CAD, and if you just make it, well, give it 3D, and then you can make these molds for creating sweet jelly. These are printers. This is a printer. Use this, and in the afternoon you use this mold and then make sweet jelly. It was really half day event. These kids, they use 3D printers and they use CAD, and they make sweet things. And when they came up with some goods, these molds, they were able to use it for cooking, preparing something sweet. This is edible jelly. We are also doing research for this edible jelly. This is a country that has won many Nobel laureates in chemistry. These are made from organic matters. We are also one of the centers of excellences for doing this. We are handling these soft gel, and then you can make this soft robot things. This can be used for regenerative medicine, for some modeling work. In the rural areas, we are again trying to create ventures. This is a pro-use 3D gel printer. The gel is analyzed. This is a 3D gel analyzer. These are the things that we are making. So far, we have the track record. This is really the amalgamation of all the cutting-edge technology. When you are trying to introduce new materials, you don't know what kind of layers, lamination you can come up with. This is a simulation. This is a modeling software dedicated for gel. You need to develop such things as well. Currently, such development has been stimulated, but now these technologies are becoming commodities. In 2 years since the start, we are now able to create these forms made from gel, intraocular lens, the IOL, and also these models of fingers with a bone in it are now available. Once you can make these things, we can ask the students to make something interesting. Some of the students are really mechanically minded. They come up with these, for instance, gears. So what can this be used? We don't really know. Creating very small model, when you go into the inside the motor, the gears shouldn't be deformed, but again, they get deformed. If you press this, then you can see that these gears may skip, and then it would not get broken. So this can be a flexible gear, might be interesting. You might be able to come up with new discoveries. on top of the cutting edge technology, we are trying to develop these things. But in the COI, we are trying to link it to open innovation. And speaking of RepRap context, regarding the 3D printer that was, they were trying to sell it at tens of millions of yen, but in our research, we are trying to make it very cheap, 100,000 yen or so. I don't really know why we are competing within the research group, but again, this is one thing. This is incorporating the RepRap of ideas, so creating many components, parts and components using a 3D computer. So once you create this 3D computer, make it available, it becomes cheaper and cheaper and cheaper. Perhaps it could lead to other open innovation. And this digital fabrication. Yesterday and the day before yesterday, before the symposium, there were meetings held, and Professor Nakayama, my favorite professor, came, and the Bio 3 printers, he is really the authority, standing at the cutting edge. In the very initial development, he couldn't get the budget. He didn't think they could create the 3D printer. The RepRap technology, among others, was something he used, and he studied the technology that he needed. That was really a kind of a shocking revelation to me. Speaking of open source, the professor is now becoming a key person, and the CIFUS has become a big venture. Even in the rural areas of Japan, Professor Nakayama, some more Professor Nakayamas should be there, and we have come up with this UFab initiative, creating such a fab in Yamagata at the station. We had this meeting. This is called Enthusiastic Elementary School. Well, this is in the Takamachi, what used to be an elementary school, and we call this a science fab. There's a venture incubation in a very rural areas. We are trying to have more startups in that space, having that 3D printer installed, and so that many people can use this. We have this project on the second floor. There are many venture companies located in this building. These venture people, they want to use laser cutter, they want to use a 3D printer, so our students go there to teach them how to use. So what happens? It's not just attracting more and more people. When you try to create this venture business, of course there is this ICT issue, but 3D printer, from ICT to manufacturing, it can serve as a bridge. Cutting edge technology can be now become available, make it available for local people. We wanted to bring this technology, the idea, to Bangladesh, from Dhaka, Bangladesh, 6-hour ride from Dhaka. This is an agricultural land, fertile land, and there in this place there are a group of enthusiastic students, and they allow them to make it their 3D printer, and there's this professor who is taking care of the orphans, supporting them through university. They are also supporting the youngsters to get employment. Perhaps the 3D printers can be used, and there is a possibility to bring 3D printers to such areas like Bangladesh, a small village. And we wanted to do this in Yamagata, using, for instance, the tourism promotion, capitalizing on the local produce. So this is a pot. These are molds for carp, and then they come up with the ideas. This is soy milk, and when you heat it, this carp from the mold melts down, and then this is already available in a carp restaurant. And this year we wanted to use Yonezawa beef. It is a consomme soup or hot jelly, and then they make it into this snow lantern shape. Again, this is already served in the local restaurant last month in the International Hotel Restaurant Show. It was exhibited, and it has been warmly received. And lastly, again, this is a local, the Western sweets maker. Again and again, he came to us. He assembled laser cutter. They designed this for their confectionery. And this is already carried in the tourism magazine called Rurubu. He is very capable of using this. He involved even the traditional, the sweet makers. And then 3D laser cutter has been used. This can be applied to many other places. Now about the tourists. In the COI symposium the other day, again, I introduced this to others. Designing such souvenir things by yourselves. And then if you can send it electronically, then perhaps the souvenirs or the sweet things that are dedicated for you can be made. Of course, the local community can use 3D printer or laser cutter to make the order-made souvenirs, so that both the cities, the metropolitan areas, and the rural areas can live side by side together. These can be utilized to the 3D manufacturing using the cutting-edge technology, and the Kansei Gakuin University, Dr. Nagata, and others. Again, Kansei or sensitivity values researchers can be used, and we would like to seek the fusion of their activities together with our activities. Thank you.